So, so today we will discuss the determining the wavelength of the mercury spectrum. It's a prominent lines, isn't it? See, so first we know about the what is the spectrometer and then mercury vapor lamp. This is a mercury vapor lamp. It's a white light. It's a emitter of various colors, isn't it? So and we know that sodium vapor lamp can be used in Larbach method, and this is the monochromatic light. It's a emit only single light. That means okay, one. And this is the spectrometer, and consists of three parts. First one colorimeter, second one is that grating table, and also measuring table. And this is the telescope. And first we do that experiment. Know about the what is the principle of the experiment? Total internal reflection. So what is the reflection? And here we do that experiment. Get some books. Just both of us okay. See, this is the grating, and this grating we have 600 lines per millimeter. Okay, what you converted it to meter, 6 lakh lines per meter, isn't it? And first we do that experiment. So first we will set the initial adjustments. So here we have vernier 0 and then main scale is 0, isn't it? And opposite side vernier 0 and main scale 180. And then you adjust that telescope 45 degree, so we get prominent colors of colors, isn't it? You go and take the reading and explain it. First to see main scale reading and then coding skills. Which color? Is the violet. The main scale reading is the 164 degree, and then coincidence is that 25 degree, isn't it? 25 minutes. And opposite vernier B 345 degrees. 340 46 degree, and then 15 minutes. And then you have to so you first completed let's say, and then let's say.
So good morning. Today we discuss about diffraction grating. So diffraction grating, as already we know that determine the wavelength of prominent colors and using the grating and the spectrometer. Yeah, diffraction grating is an arrangement of identical, equally spaced parallel lines rolled on glasses. And a typical diffraction grating will have something like 600 lines per millimeter, and this is the grating, and the diffraction grating are used to produce the optical spectra. And the light of wavelength lambda normal to the grating, so the each clear space ABC acts like a very narrow slit and produces its own diffraction. The light is from the same monochromatic source and therefore it is coherent. and the consider light which diffracted by each slit at the same some angle theta to the normal, like this. And then secreting that theta 1 theta 2, and the slits are equally spaced though that angle theta produces light that phase A and B, so therefore positively reinforces. So then the light will also in phase from every other slit, and also produce a positive reinforcement. And the when the waves reinforce each other, the path difference an is a full number of wavelength, and that means an equal to n lambda. Already we know that n is the whole number, and that an equal to d sine theta, and d sine theta equal to n lambda. And the diffraction grating, the angle theta will be slightly different for each wavelength of light, and so the grating separates the white light into its spectrum and does this much more effectively than the prism. So the light needs to be focused with the eyepiece lens of a telescope or a spectrometer, so after that emerge from the grating. And diffraction grating with a large number of lines produces a very sharp maximum and completely destructive interface at other angles. And calculations, yeah, diffraction grating has a 600 lines per millimeter, so such a grating illuminated with the yellow light at 6 into 10 power minus 1 meter. So calculate the angle at 0 first order and second order. Diffraction will be observed, and then we using the formula for lambda equal to sine theta by n m, and we get the wavelength of prominent colors. Thank you.